All right, sorry for the delay, everyone. We're about to start with our next talk about the sharding of rollups. Please give it up for Ilya Marozau.
Hi everyone. So my name is Ilya. I'm a senior protocol researcher at TUM Foundation and security researcher at Munich. I focus on cryptography and decentralized algorithms. So today we talk about sharding of rollups, and motivation for this talk actually is that we go first understand what is sharding. We understand how sharding can be used, and see possible future development of decentralized application, especially on top of TUM. As well as agenda, we talk about sharding and what is sharding, what's the role of sharding, challenges and design principles, and the upscaling. Yeah, we'll try to talk about this within 20 minutes. So first of all, what is sharding? And probably most of you are familiar with the case of what is database sharding. It's just actually splitting your actual data into two, for example, or several portions or between different databases. But what is decentralized network sharding? And the idea of decentralized network sharding is that you can take a number of parallel chains and actually run them together in a serial execution environment. The biggest benefit of all the system is that these shards operate with each other as it would be a single system. So sharding is just multiple chains. And what is the problem we want to solve with sharding? Why we talk about this today? First of all, scaling. Scaling of your state, of your chain, and scaling of your execution. Second, sharding brings decentralization to a system, because in general, sharding makes no sense without decentralization. Also, application scaling, and my favorite one, improvement of utilization efficiency. Quite volatile term, but what does it actually mean? Imagine you have Ethereum with 1 million validators. At any moment of time, only one of around 2 million actually perform their useful work, actual trustless computation. And sharding is a way to improve this efficiency. But why sharding? And the reason why sharding first, because sharding environment is unique. It gives you a property of 401 and all, and 1 for all. This is very interesting property because all the shards treated as a single system, and every shard is the whole system. I will explain you later why, but this is a very beautiful property that gives you extra security, chip of the system, and interoperability. That is actually the next one. Okay, so protocol and build communication, because most of the solutions like aggregation layers, elastic chains, like communication protocols like layers that are built on top, we have it inbuilt in protocol. And interoperability and interchangeability. This is important property because actually it's like troopers from Star Wars. You kill one, all the others will continue to fight, and can take a bit more work for them. And let's first of all try to understand how normal validity rollups work. Yeah, this is a common schema. First of all starts from mempool, then sequence them in a single non-validated block, then block.
It's slightly easier if you face away from the microphone. Yes, from the speakers.
Okay.
Yes.
Yeah, okay, sorry. And that show.
I think I see the issue.
Okay.
When we're setting this up, you're supposed to face it slightly above.
Okay. And so actually when we have
I think you can come here a little bit. Yeah, I think we should do that.
yeah,
There we go.
Okay, maybe I can stay.
Yeah,
cool. So and then we have a validation, and sometimes it's called executor. Then executor updates the states, send the block to the relayer. Relayer takes the state diff, depending on what is public input, we request prover to generate a validity proof, send validity proof to settlement layer, and data to GL. So now each component will try to understand how we will actually shard the system. And we start with sequencing. And sequencing in sharded system requires you only one single thing. Please send the transaction to a special shard unit. And this is a simple request, like shards are like chains. In general, they share the same main pool. But we want these transactions will be included in the block that are actually responsible for these transactions. And this is very simple problem. In general, what we researched, one of the best possible solution, is use PBS system sharded with L1 and L1 searchers and builders. This is very simple and concise solution. Because how to distinguish that you understand like where to send your transaction. In general, you use address. Target address tells you where the target shard will be used. So that's why if your transaction is compatible, you can use PBS from L1 for additional math. Yes, that means that math goes to L1, but in general, you have extra liveness from L1 chain and decentralization. So this is one of the best way for our sharded rollups to operate with sequencing. Then go to validation. And you can see that actually every shard operates independently. They have their builders, proposers, they have their own state, and state is not shared. And they have their own subset of validators. And actually, that system actually runs in parallel. I mean, proposers are independent, stay independent storage. So actually, they can do work in parallel. And the funny thing with validation is that we have consensus. And this is system when you have two different consensus. On sharded system, consensus first is called local one. And local one is responsible for a single shard consensus. But global one is responsible for a beacon shard. And now I'll explain what is beacon shard, sometimes called coordination shard. On almost every, I know only sharded systems that have always a coordination shard. This shard performs very important role. This shard and data in chain shared across all validators. This is a single shard that has this property. And this shard plays an important role. First, it keeps state rules of all shards. That allows you actually to share information very quickly. And second, that all validators will validate the beacon shard. That's why you can use, for example, more relaxed consensus solution. For example, for local consensus, we use hot stuff 1, while for the beacon we use hot stuff 2. And during this simple combination, we can achieve better property for the whole system. And again, beacon shard is one that is responsible for security of the system. You can see this tiny arrows with rollup plot. And now I explain you how it works. And the most fascinating stuff, how rollbacks happen on sharded systems. On sharded systems, rollbacks happens not on a single shard, it happens on the whole system. And here, where main shard or beacon shard played the most important role. Because when shards, execution shards, submit their states, at some moment of time, if one of them is compromised, the whole consensus will see this problem. And they will roll back main shard. So first we start with roll back the main shard. That means that all the execution shards at the same time will roll back to the state that was saved on the main shard at this moment. And this is very fascinating stuff. And in general, if you, as a actually shard, see that my blocks were fine, what you do, you actually just execute the blocks that will later compose. So you don't need to actually totally roll back your blocks. You roll back only the state and re-execute the block. But why you are actually did? Because why everyone roll back? Because of communication. If, for example, malicious shard was compromised to send messages to all the other shards, we want to roll back all of the other shards because message affected their state change. And this is very important property, and this is very heavy security guarantee because the whole system is secure as a single shard. So if any single shard is malicious, it cannot actually break down the whole system. The whole system will just say, like, you are punished, a subset of validators is punished on the shard, and the system roll back. And okay, we still roll up, so what we do with DA and validates rollups And this is very interesting stuff because, as I said, shards are parallel, but they still has to be synchronized in some manner. And this is where actually we call it synchronization committee, strange naming, but some of the projects call it state committee. The reason is to have some servers, decentralized servers, that actually responsible for aggregation of the state changes on the shards. We call like this SD, as always type of SD, state diffs. Aggregate the state diffs on your shards and actually submit the corresponding data availability to one. And same happens with the proof. Because remember that when we roll up, also here roll up, we prove the state for the data that we submitted. Yeah, we cannot submit like 10 blocks and say like, oh, these validated proofs on the 5 and we are now. No, that will not work. And that's why we have to track which data we send for one. And this is very tricky schema. How in general sharded rollup work? This schema can be quite complicated at first view, but I'll explain quickly what it means. In general, execution shards send their KZG commitment of the data availability to beacon shard. And this is where beacon shard plays a role of settlement layer for execution shards. Yeah, actually, you send your state transition proofs and data availability commitments, well, like KZG commitment, yeah, to beacon shard. And beacon shard verifies state transition proof. And this is a simple idea of aggregation of proof through execute trustless execution on beacon shard. Beacon shard can check all the proofs and submit a single proof aggregated to one, while at the same time each execution shard will submit their data availability to blob storage. And then the last stage, we just combine all together. We take the main shard state proof and data commitments from execution shard, and we're done. So this is quite beautiful schema, but at the same time, it works very fast because beacon shard has same block production speed as execution shard. And a few words about cross-shard transactions, or what we call messages. I mentioned at the very beginning. Messages differ a lot from cross-chain messages, cross-chain transactions look at. Because first, they have censorship resistance. They have an order processing, they cost very low. I mean, in general, our cost of message is around 5,000 gas. It's very cheap. And they also have context saving. And this is fascinating stuff because I mentioned at the beginning we have a single execution running. This is main idea of sharding. In sharding, you have a single execution running. That means when you execute something on one shard and want to delegate the call to another shard, you actually save part of your context and actually delegate it to another shard. This is what actually called a sort of asynchronous composability, but I explain it in the next slide. And important stuff about messages that can be emitted only by smart contracts and time to delivery can be quite predictable because it takes only 2 blocks, block emit and block target. Network delay, that is very small because in general, subset of validators quite small, and we try to keep the network in general. It's a good idea for sharding your network like a full graph. And congestion. Yeah, congestion, unfortunately, we cannot predict, but fee model designed differently. And fee model allows you to make some priority for messages to reduce the congestion of messages in favor of a bit more congestion to transactions. And yeah, now we have asynchronous environment. And I propose you to think now about shards not as a chains, but as a processing units. So you can see that actually they can work independently, like validators work independently. So you can imagine this like a computer core with like 32 cores, 64 cores that can actually send transactions between each other. And this is very fascinating stuff because when you have a synchronous environment with quite strong properties, quite strong protocol guarantees, you can truly develop other like scalable applications. And what I mean scalable, imagine like, can we actually have, for example, some scientific computations on Ethereum? And quite likely no. And not because it's like expensive, but because actually how fast you can process a large amount of data. a lot of amount of computations. And this is where sharding wins. Because for the sharding, it's more profitable if you can have multiple computations in parallel and just aggregate some results after end. This is actually some idea of decentralized algorithms can come into play. And simple example of such scalable application is like DEX. Imagine that actually if you have a single environment, you can build a DEX with a bit different approach. Let's say that now you have pools that deploy on different shards. And this is what actually you cannot provide, for example, with like different rollups or even aggregation layers. Now, I can deploy different shards on different pools on different shards. And if I do it correctly, for example, this is first 3 pools on Uniswap that share actually around 50% of the whole load on Uniswap. If you properly split them across shard, the whole, like statistically, you will see that actually the load will be quite properly distributed across all the shard. If user on shard A needs to exchange USDC and USDT on different shard, there will be just a small cross-shard message. Otherwise, the load will be on its own shard. And all that actually reduce the load on a single application. And the whole system starts to work like a distributed environment for the applications. And this is actually how we can move forward with development of scalable system, or what sometimes people in crypto say composability. And this is like composability between shards.
You can join twice. You have so we're going to do, I think, 10 or 11 questions. You know the drill, right? For